Welcome to The Explainer. Today, we're going to pull back the curtain on the hidden rulebook that makes our entire digital world tick, from sending a simple message to streaming an entire movie.
I mean, it feels like magic, right? One second you hit send, and the next it's on the other side of the planet. But sending any kind of data, an email, a video call, whatever, it's not magic. It's actually a really complex journey, and it's governed by a universal set of rules that every single device has to follow.
And that set of rules, well, it's called the Open Systems Interconnection Model, or just the OSI model for short. Now, it's not a piece of hardware or software. It's a way of thinking about the problem. It breaks down the huge task of network communication into 7 distinct, manageable layers. You can kind of think of it like a 7-story building for your data.
So let's take a little tour of this building, starting right from the ground floor. We're going to look at the actual physical wires, see how data gets delivered both locally and globally, then figure out how our apps have a coherent conversation. And finally, we'll see why this whole model still matters so much today.
All right, we're starting at the very bottom. Layer 1, the physical layer. This is all about the stuff you can actually touch, the tangible hardware that's responsible for sending the raw bits of data, the ones and zeros. So the key takeaway here is that this layer deals with things you can physically point to, the cables, the connectors, the electrical signals, or even the pulses of light that represent all our digital info. If this layer fails, well, nothing else matters. It's literally like having an unplugged cord.
And that medium is just the pathway the data travels on. It could be the Ethernet cables snaking around your office, or it could just as easily be the invisible Wi-Fi signals zipping through the air in your house.
This is a perfect illustration of how that physical media has evolved. We went from older copper coaxial cables, which send electrical signals, to these incredible modern fiber optic cables that flash pulses of light at, light speed, carrying way, way more data.
Okay, let's head up to the next floor, Layer 2. Now we're going to see how things build on top of Layer 1. We're taking all those raw bits and starting to organize them for local travel. Think of it like sorting mail for a single neighborhood.
So, the data link layer bundles those bits into organized packages called frames. Then it uses a unique hardware address, you've probably heard of it, the MAC address, to make sure that frame gets to the right device on your local network. This is so your print job doesn't accidentally get sent to your smart TV instead of your printer. Super important. So we've turned bits into frames, and now we're ready to leave the local neighborhood. This is where the internetwork part of the internet really comes alive, right here at Layer 3, the network layer. And this slide just nails the difference. If Layer 2 is the local mail carrier who knows every house on one street, Layer 3 is the entire global postal service. It uses logical IP addresses to route data packets across thousands of different networks to get them literally anywhere in the world. As we move up to the top 4 layers, the focus kind of shifts. It's less about the physical journey of the data and a lot more about making sure that data is reliable, that it's formatted correctly, and that it's actually useful to the applications we're trying to run. These 4 layers really work together like a well-oiled machine. You've got the transport layer acting as a sort of quality control, making sure everything arrives okay. The session layer manages the conversation. The presentation layer is like a universal translator for data. And then, finally, the application layer is the one we actually see and use. So, for example, Layer 5, the session layer, that's the hero that lets you resume a huge download that died halfway through. By setting these little checkpoints, it saves you all that frustration of having to start over from scratch. It's an absolute lifesaver. And here we are at the top of the building, the application layer. This is home to all the protocols we actually recognize. Things like HTTP, which our web browsers use to pull up websites, and SMTP, which powers the very email that kicked off our entire journey through these 7 layers.
So we've gone all the way from physical bits to our actual applications. But here's the big question. Why does this abstract model, something dreamed up back in the 1970s, still matter so much in our world today?
Well, it's because this layered approach gives everyone a universal language for networking. It allows engineers to design incredibly complex systems that can all still talk to each other. And maybe more importantly, it's a fantastic framework for troubleshooting. If your internet's down, you can check layer by layer. Is the cable unplugged? That's a Layer 1 problem. Are you on the wrong Wi-Fi? Layer 2. A bad IP address? That's Layer 3.
And what's really fascinating is that while the specific protocols the OSI group actually created were mostly replaced by the simpler, more practical TCP/IP model that we use today, the 7-layer framework itself ended up being this indispensable tool for teaching and for diagnostics. It kind of succeeded by failing, which is pretty cool.
And that kind of leaves us with a final thought to chew on. As our world gets more and more connected, with billions of smart devices and AI-driven networks, is this 7-layer model going to be enough? Or are we going to have to add a new floor to our digital skyscraper?
Welcome to The Explainer. Today, we're digging deep. We're going past all the software, all the apps, all the code, and getting right down to the foundation of our digital world, the raw hardware and the actual physics that make it all possible. Let's get into it. I mean, have you ever really stopped to think about it? That video you're watching right now, it started as a bunch of data on a server that could be thousands of miles away. How in the world did it get from there, across oceans and continents, to pop up on your screen almost instantly?
Well, it might feel like magic, but I promise you, it's not. It's an incredible combination of physics and really clever engineering. And that whole amazing journey begins at the very, very bottom, the most fundamental layer of any network. So, let's start there. Section 1. From bits to a pulse. You see, before any of your data can go anywhere, it has to be changed from the language of computers, ones and zeros, into a real physical signal. And it turns out there's a very specific rule book for how that happens.
That rulebook is called the OSI reference model. Think of it like a universal blueprint for how networks talk to each other. It's a 7-layer framework that makes sure a device made in one country can talk to a server in a totally different country, no problem. It just organizes the whole complicated mess into logical steps.
Now, there are 7 layers, but we're going to ignore all the others for now and go straight to the bedrock. Layer 1, the physical layer. This is where the real translation happens. This is where those abstract digital bits get turned into electrical pulses, or flashes of light, or even radio waves. It is literally the bridge between the digital world and the physical one. Okay, so how does this actually work? That brings us to Section 2, the 4 physical rules. For any 2 gadgets to talk to each other on this level, they have to agree on 4 fundamental things.
Honestly, the easiest way to wrap your head around this is to think about a simple power outlet, right? For your phone charger to work in any wall socket, the plug and the socket have to agree on the basics: the shape, the amount of voltage, what each little prong is for, and the right way to plug it in. The physical layer works on those exact same principles.
First up is the mechanical rule. This is purely about the physical stuff. What's the shape of the connector? How many pins does it have? It's the reason an Ethernet cable won't fit into a USB port. It sounds obvious, but if you get this first step wrong, nothing else even matters. Next, you've got the electrical rule. So, okay, the plug fits. Great, but what about the actual electricity? This rule defines the voltage levels, like what voltage means a 1 and what means a 0, and also the data rate, which is how fast those signals are flying back and forth. If you get this wrong, best case, they don't understand each other. Worst case, you could literally fry the hardware.
Then there's the functional rule. This one is all about purpose. It specifies exactly what each individual pin or wire is supposed to do. Back to our power plug, this is knowing which prong is live, which one's neutral, and which is the ground. For a network cable, it's about knowing which pin sends data, which one receives it, and so on. It makes sure everyone's having the right conversation on the right line.
And finally, we have the procedural rule. This defines the correct order of operations. You know how you plug something in before you flip the power switch? Networks have a proper sequence too for turning connections on and off. Get the order wrong and the whole thing fails. So mechanical, electrical, functional, and procedural, all 4 have to be in perfect harmony for communication to even start. So now that we have the rules of the road, what are the roads themselves? That takes us to Section 3, data's journey through wires. Let's look at the actual physical stuff. The highways our data signals travel down. First up, we have coaxial cable. You might recognize this from an old cable TV or internet setup. What's cool here is its design. You've got that central copper wire carrying the signal, then it's wrapped in insulation, and around that is a braided shield to protect against electrical noise, all wrapped up in a tough outer jacket. It's a pretty smart layered design.
Now, what's way more common these days, especially in an office, is twisted pair cabling. And it basically comes in 2 main flavors. You've got UTP, or unshielded twisted pair. That's the standard stuff. It's cheaper, it's flexible. Then you have STP, shielded twisted pair,
which adds a metal shield for way better protection against interference. It costs more, but it's what you'd want to use in a factory with heavy machinery that could mess with the signal. But for the absolute best performance, for pure speed and distance, data stops being electricity altogether. Instead, it travels as tiny pulses of light, zipping through incredibly thin strands of glass in fiber optic cables. This is the real backbone of the modern internet. And this is just so cool. Check this out. This shows how that light actually travels. On the left, in what's called step index fiber, the light just bounces off the walls in these sharp zigzag patterns. But on the right, in graded index fiber, the glass itself is engineered to gently bend the light into these smooth flowing curves. And what that means is you get a cleaner signal that can go way, way farther without getting distorted. It's a really elegant piece of engineering.
Of course, data doesn't always need a physical wire to get around. And that brings us to Section 4, information riding the airwaves. Yep, we're talking about wireless.
This picture lays it out perfectly. A wired network up top is a physical point-to-point connection. It's a road. A wireless network on the bottom is more like a broadcast tower, sending signals out through the air that any device in range can pick up. Now, these radio waves aren't just all one big jumble. They're organized into different frequency bands. If you look, way down at the lower end, you've got your AM radio. Move up a bit, you pass things like FM radio and TV signals. And then you hit this sweet spot right here, the UHF, or ultra-high frequency band. That's where our cell phones and Wi-Fi live. Go even higher, and you're in the realm of satellite communications.
All right, so we've covered the rules, the wires, and the airwaves. Let's put a bow on this in Section 5 and talk about why this layer, the one we never even see, really matters.
So what's the big takeaway? It's this. Every single thing you do online is built on this physical foundation. The type of fiber optic cable buried under the ocean determines global internet speeds. The specific Wi-Fi frequency your router is using affects how well your movie streams. The physical layer might be invisible to us, but its impact is everywhere, in every single click and download.
Our entire connected world is woven together by these physical cables and invisible waves. But our appetite for data, it's just exploding. We want 8K streaming, virtual reality, the metaverse, instant everything. And that makes you wonder, what's next? What new wire, what new frequency, what new physical technology is going to power our future? That's something to think about. Thanks for tuning in.
You know, we're constantly surrounded by digital information, right? But have you ever really stopped to think about how that chaotic mess of raw data, just flying through our tables and airwaves, actually turns into something we can use?
I mean, seriously, think about it for a sec. How does a total jumble of ones and zeros, traveling as flashes of light or little zaps of electricity, somehow organize itself into the movie you're streaming right now or the website you're scrolling through? It's not magic, but it is an absolute masterpiece of organization. And it all starts way down at the very bottom of the network stack. So everything begins at the physical layer. This is all the hardware stuff, the cables, the radio waves, you name it. And really, it's just a fire hose of raw data. It's blasting out ones and zeros with absolutely no structure, no context, and zero guarantee that they'll even arrive correctly. It is just pure, unadulterated digital chaos. And that, right there, is the core problem we have to solve. On one side, you've got this raw, totally unreliable stream of bits coming from the physical layer. But on the other side, what we want, what we need, are organized, reliable units of data. So how in the world do we get from that chaos to actual order?
Well, we get there thanks to the hero of our story today, the data link layer. I want you to think of this layer as the network's super meticulous organizer. Its entire reason for being is to step in, take that chaotic bit stream from the physical layer, and somehow transform it into a reliable, orderly connection.
So how does it pull off this organizational miracle? Well, the first and probably most fundamental thing it does is something called framing. Imagine you just found a giant, disorganized pile of loose leaf paper. The very first thing you do is sort all those pages into neatly labeled folders, right? That is exactly what framing does for our data.
And the concept is pretty brilliant in its simplicity. First, the data link layer just listens to that raw stream of bits coming in from all the hardware. Then, it literally just chops up that endless stream into these discrete, manageable little chunks. And these chunks are new folders for data. They have a special name. We call them frames. And here's a great, concrete example of what one of those looks like. This is a 53-byte ATM cell. See? It's not just random data anymore. It's got a structure. You can see there's a 5-byte header. That's kind of like the label on our folder.
And then there's a 48-byte payload, which is the actual data tucked inside. This structure is absolutely everything. Okay, so our data is now neatly organized into frames. That's a huge step. But, organized data is pretty useless if you don't know where to send it. And this brings us to the second core function, physical addressing. To get this done, the data link layer adds that header to the frame. And inside that header, it puts the physical address, which you probably know is the MAC address for both the sender and the receiver. It's exactly like putting a to and a from address on an envelope. This makes sure the frame gets to the right machine on the local network. And hey, if the frame is actually meant for a system outside this network, the receiver address just points to the router, which is the device that'll send it on the next leg of its journey. Okay, so we've got organized frames and we've got addresses. We're looking good. But the physical world, it's a noisy place. Wires can get interference. Signals can get weak. So what happens if our perfectly addressed little envelope gets corrupted on its way? Well, that is why the third critical function is error control.
And the most common way to do this is with a really powerful technique called a cyclic redundancy check, or CRC for short. Here's the gist. The sender runs a quick mathematical calculation on the data in the frame and just attaches the small result, kind of like a checksum. Then, when the frame arrives, the receiver runs the exact same calculation. If its result matches the sender's, awesome, the data is good. If not, the frame is considered corrupt and it just gets thrown away. Conceptually, the math behind it is kinda like long division, but for binary data. The sender sends the data along with a calculated remainder. The receiver does a similar calculation, and if the final result isn't 0, it knows right away that an error has crept in somewhere. It's just an incredibly clever and efficient way to make sure our data is intact. All right, so we've got frames, we've got addresses, and we've got error checking. But how does this all actually play out in the real world, like on the local area network in your home or your office? Well, it turns out that for LANs, this layer is so important that it's actually split into 2 specialized sublayers. And these 2 halves are the Logical Link Control, or LLC, and the Media Access Control, or MAC. They're a team, and they work together, but each one has a very, very specific job to do. So you can think of the LLC as the manager. It's the one responsible for flow control, making sure a really fast sender doesn't just overwhelm a slow receiver, and it also handles that error checking we talked about. The MAC sublayer, though, that's the traffic cop. On any shared network, whether it's a Wi-Fi channel or an old-school Ethernet cable, only one device can talk at a time. The MAC layer's whole job is to manage who gets to speak and when, preventing a mess of data collisions. And this is a perfect example of that MAC layer in action. For wireless networks like Wi-Fi, where it's kind of hard to hear if a collision happened, the strategy is collision avoidance. All the devices listen really carefully, and they try their best to avoid talking over each other. It's very polite. For wired Ethernet, though, the strategy is collision detection. The devices are a bit more aggressive, they just go ahead and talk. If a collision happens, they detect it, back off for a random amount of time, and then they try again. Just 2 different strategies for solving the exact same fundamental problem. So, when you put it all together, the data link layer is really the unsung hero of networking. It takes raw, chaotic bits and organizes them into frames. It adds physical addresses so they know where to go locally. It checks for errors to give us that reliability we need. And it plays traffic cop to manage who gets to use the network. It literally brings order from chaos. There's a great quote from our source material that just nails it. The physical layer provides only a raw bit stream service. It's the data link layer that actually makes that physical link reliable. Without this layer, our entire digital world would just be an unusable mess. It really makes you wonder, what other invisible, brilliantly designed systems are working tirelessly behind the scenes every single second of every day just to make everything we take for granted work? Thanks for joining me. Have you ever really thought about what happens when you hit send on an email? How does it get from your screen to someone else's halfway across the world in like a second? Well, today we're pulling back the curtain on the magic behind it all. We're talking about the internet's global postman, the network layer. Seriously, think about that question. It feels like magic, right? But it's not. It's an incredibly complex yet elegant system working flawlessly behind the scenes. This invisible network is what makes our modern world tick. It lets us connect with literally anyone, anywhere on the globe. All right, so the secret sauce here is what's officially called the network layer. You can think of it as the brain of the internet's delivery service. It has 2 really, really important jobs. First, logical addressing, which is just a fancy way of saying it gives every single device a unique address. And second, routing,
which is all about figuring out the absolute best path for your data to travel from point A to point B.
But you know what? Let's ditch the tech jargon for a minute. The absolute best way to get your head around the network layer is to picture it as a massive, planet-spanning postal service. It takes your digital packages, we call them packets, reads the address, and makes sure they get delivered no matter where in the world they need to go.
So sticking with that postal service idea, every piece of mail needs a specific address, right? A house number, a street, a city, a zip code. Well, it's the exact same thing online. Every single digital packet needs a unique IP address. That's the logical address we just mentioned. It's the one-of-a-kind destination code for every phone, computer, and smart fridge on the internet. And when a message is sent from just one computer directly to one other computer, there's a name for that. It's called unicast transmission. It's basically the digital version of sealing a letter in an envelope and sending it to one specific person's mailbox. That unique IP address makes sure your data ends up exactly where it's supposed to and nowhere else.
Now, here's a fun problem. As the internet just exploded in popularity, we started running out of addresses. The original system, called IPv4, only had about 4.3 billion of them. Sounds like a lot, but it wasn't nearly enough. So we had to invent a new one, IPv6. And get this, IPv6 has 340 undecillion addresses. That is a 340 with 36 zeros after it. It is a number so big, we could assign an IP address to every single atom on the surface of the Earth and still have addresses left over. So yeah, I don't think we're going to run out again anytime soon.
Okay, so we've got the addresses covered. But who's doing the actual sorting? What are the post offices of the internet? Well, that's where this little box comes in, the router. You've probably got one in your house. These things are the backbone of the entire internet. They're the smart post offices that connect all the different networks together and decide where to send every single packet of data.
So how does it do it? It's like a super fast 4-step dance. Step 1, a packet arrives. Step 2, the router reads the destination IP address, just like a mail sorter reading a postcard. Step 3, it looks at its own internal map of the internet to find the best way to send it. And finally, step 4, it forwards the packet on to the next writer in the chain. It's simple, but it happens millions of times every second all over the world.
And here's where it gets really cool. This isn't a static system where the paths are set in stone. No way. All these routers are constantly chatting with each other, giving updates on network traffic. If one path suddenly gets super busy, think of it like a digital traffic jam, they'll instantly find a new, clearer route for your data. It all happens automatically to make sure things are as fast and efficient as possible.
Now, our digital post office actually has two main ways of delivering the mail. And this quote from our source material sums up the first method perfectly. It's called a connectionless service. You basically just slap an address on your data, toss it into the system, and trust that it'll get there. Let's go back to our mail analogy. Connectionless service is like sending a postcard. It's super fast, very little fuss, and great for things like a video call, where if one tiny little packet gets lost, you won't even notice. The other option, connection-oriented service, is like sending certified mail. It actually establishes a dedicated, reliable path before sending anything to guarantee it gets there safe and sound. This is what you need for things like downloading a file, where every single bit counts.
And this right here is the absolute core of it. The network layer is the invisible thread that stitches together thousands upon thousands of separate, independent networks, your home Wi-Fi, your cell provider, massive undersea cables, and makes them all work together as one single global internet. It hides all that mind-boggling complexity so we can just use it.
And, of course, the system is always evolving. To handle that big switch from the old IV4 addresses to the new IV6 ones, engineers came up with some really clever tricks. One is called tunneling. It basically wraps a new IV6 packet inside an old IV4 packet, kind of like putting it in a disguise so it can travel through older parts of the internet. It's a perfect example of building the future on top of the foundations of the past.
So, from unique IP addresses acting like street numbers to brilliant routers acting as smart post offices, the network layer is the unsung hero that powers our digital lives. But it does make you wonder, right? As we connect billions more devices, from cars to coffee makers, and as we demand more and more speed, what's the next big challenge for our global postman? What comes next?
Hey everyone, and welcome. Today we are diving into one of the most critical yet totally unsung heroes of the internet, the transport layer. It is, no joke, the reason our digital world actually works the way we expect it to. I mean, really think about that for a second. You hit download on some massive file, or you start streaming a 4K movie. How in the world does all of that data travel across the wild, chaotic internet and just reassemble itself perfectly on your screen? It seriously feels like magic, but it's not. It's just some really, really clever engineering.
Because, without a system in charge, you'd get exactly what you'd expect, a complete and utter jumble. Data packets would be arriving all out of order, some would be corrupted, and some just wouldn't show up at all. That file you downloaded? A garbled mess. Your movie night? Totally unwatchable. It would be pure digital chaos. And this is the solution to all that chaos, the transport layer. You'll also hear it called Layer 4 of the OSI model, which is kind of like a universal blueprint for how networks should communicate. Its entire purpose, its reason for being, is to provide a reliable, orderly delivery service for all the apps you use every single day.
Honestly, the best way to picture the transport layer is as this super organized, maybe even slightly obsessive manager. It doesn't carry the data itself, but it oversees the entire process from shipping to receiving, making absolutely sure every last piece arrives safe and sound.
And where it sits in the whole network setup is just so important. See, it's sandwiched right between the application layer, that's where your browser, your email, your games all live, and the internet layer, which just handles the basic job of getting packets from point A to point B. The transport layer is the essential bridge that lets your apps actually use the internet reliably.
So what's on this digital manager's to-do list? Well, it operates based on a really strict set of rules, all designed to guarantee reliability from the moment a connection starts till the very end. Let's break down its key jobs.
First up, we've got packet sequencing. Okay, so a big file is way too big to send in one piece. So the transport layer chops it up into smaller chunks called packets. And here's the crucial part. It numbers every single one. It's like taking a long letter, numbering each page before you mail it. That way, even if the pages arrive all mixed up, the person on the other end knows exactly how to put them back together in the right order. Simple, but brilliant. All right, what about error handling? What happens if one of those pages gets lost in the mail or the ink gets smudged? Well, the transport layer has a plan for that. It has the receiver send back little messages called acknowledgements, or ACKs, for every packet it gets. Now, if the sender is waiting and doesn't get an ACK for, say, packet number 5, it just assumes it got lost and sends it again. It's basically the system saying, hey, did you get page 5? Nope. Okay, sending another copy right now. Next is this absolutely critical function called flow control. See, you can't just blast data at another computer as fast as you possibly can. What if the device on the other end is an older phone, or it's just busy doing 10 other things? It could get completely overwhelmed. Flow control is this really elegant system that stops a fast sender from totally drowning a slow receiver. And this is a perfect illustration of how that works. It's a process called back pressure. If the receiving computer starts to get bogged down, the transport layer sends a signal back to the sender that pretty much says, whoa, slow down a bit, my inbox is getting full over here. This is what prevents data from getting dropped and keeps the whole connection nice and stable. So how does the transport layer keep all this, the sequencing, the error checking, the flow control, organized for just one conversation, like your file download? It uses something called a virtual circuit. Before any data gets sent, the two computers establish a connection. Now, this isn't a physical wire. It's a logical, managed session that makes it feel like they have a private, dedicated line just for their little chat. This diagram shows it perfectly. Look, the packets going from host 1 over to host 5 might physically take different routes through the network. Some might go through switch B, others might zip through E. But because they're all part of the same virtual circuit, the network treats them as one single orderly stream of data. This guarantees they all get put back together correctly on the other side. It's just such a clever way to create order out of potential chaos. Now, we've been talking about the transport layer as this big concept, this set of rules. But the actual heavy lifting is done by specific protocols. And there's one in particular that is the true workhorse of the modern internet. So let's meet TCP, or Transmission Control Protocol. If the transport layer is the manager, then TCP is the star employee. It's the one that diligently follows every single rule we just talked about, the sequencing, the error checking, the flow control, the whole shebang. It's the protocol that makes the internet feel as reliable as it does. The secret sauce for TCP is that it's connection-oriented. Think of it like making a phone call. You establish a connection by dialing, you have your conversation, and then you hang up. It's a confirmed two-way street. The other approach is connectionless, which is more like dropping a postcard in a mailbox. You just send it and hope it gets there. That's for things where speed is everything and a few dropped bits don't matter, like in live video streaming or online gaming. But for things where every single byte has to be perfect, like a web page or a file download, you absolutely need a connection-oriented protocol like TCP. It's all about using the right tool for the right job.
Okay, so we've gone through all the technical details. Let's pull back and bring it all together. Why is this invisible manager so incredibly important to our everyday digital lives? Well, in a nutshell, this is everything the transport layer does for you, personally. It makes sure you get the whole file, not some corrupted piece of junk. It manages the connection speed so that everything just feels smooth. It puts web pages, video calls, everything back in the right order. It silently fixes errors without you ever even knowing they happened. And maybe most importantly, it makes sure the data from your Zoom call goes to the Zoom app and not to your email. That last bit is called multiplexing, and it's essential for doing more than one thing at a time online.
And this quote just boils it all down to its beautiful, simple essence. While other layers are busy routing packets to the right computer, the transport layer does that final, critical job. It gets those packets to the correct application on that computer, reliably and in order.
So, the next time you're streaming a movie or downloading a big file, just take a second to appreciate the silent, meticulous work of the transport layer. It's that invisible manager turning the internet's raw chaos into the reliable, orderly experience we all completely depend on. Seriously, what do you think would be the first thing to break if it just disappeared? Something to chew on. Thanks for joining me.
All right, let's talk about the internet. You click, you tap, you swipe every single day, right? Connecting to, well, everything, without even thinking about it. But have you ever stopped to wonder how that actually works? That's what we're diving into today. The hidden architecture, the genius system that makes our entire digital world tick.
I mean, really think about it for a second. You click on a link and boom, information from a server that could be thousands of miles away just appears. It feels like total magic, doesn't it? But it's not. It's actually a beautifully tuned machine, and we're about to pop the hood and see how it all works.
You see, like any complex system, the internet isn't just chaos. It runs on a surprisingly logical and incredibly organized system of rules. And in the world of networking, these essential rules are called protocols.
So, what exactly is a protocol? Well, the best way to think about it is like grammar for a language, right? If you and I want to have a conversation, we need to agree on the rules of English. It's the exact same deal for computers. For them to exchange any information at all, they have to speak the same digital language, and that language is defined by these things called network protocols.
And believe me, these rules are super specific. We're talking everything from the timing of the conversation to the size of each message, how it gets encoded into signals, and even how it's packaged up for the journey. Every single little detail has to be standardized for a global network like this to even function. So, to keep all these rules from becoming a jumbled mess, engineers came up with a universal framework. It's called the OSI model. You can think of it as the master blueprint for all network communication, and it breaks the whole complicated process down into 7 distinct, much more manageable layers. Let's start at the top and see how it works. We're going to start at the very top, with layer 7, the application layer. This is the only part you actually see and interact with. When your web browser uses something called HTTP, that's Hypertext Transfer Protocol, to go grab a web page, that's the application layer doing its job. It's basically the bridge between you and the rest of the network. Right below that, you've got layer 6, the presentation layer. This one's like the network's universal translator. It grabs the data from your app and makes sure it's in a format that the computer on the other end can understand, no matter what kind of system it's running. This is also where really important stuff like data encryption happens, scrabbling your data to keep it secure. Okay, now we get to layer 5, the session layer. And honestly, this is one of the smartest parts of the whole system. Think of it as the conversation manager. Imagine this. You're downloading a huge file, maybe a 2,000-page document. What the session layer does is super clever. It adds checkpoints, or what we call synchronization points, into that data stream. So maybe it puts one after every 100 pages. Now, if your connection suddenly dies while you're on page 523, you don't have to start all the way from the beginning. No way. You just pick back up from the last checkpoint at page 500. It's an absolute lifesaver, and it's what keeps those long conversations between computers stable.
Moving down to layer 4, we have the transport layer. I like to think of this as the network's quality control department. It takes big chunks of data from the upper layers and chops them into smaller, numbered pieces called packets. Then, its job is to make sure every single one of those packets gets to the destination, in the right order and with no errors, before it puts them all back together again.
Underneath that is Layer 3, the network layer. This is basically the Internet's postal service. Every single packet gets a destination address, and this layer's whole job is to look at that address and figure out the most efficient route for it to take across this massive, tangled web of networks we call the Internet.
We're getting closer to the actual hardware now. Layer 2 is the data link layer. This layer handles communication between two devices that are directly connected, like your computer and your Wi-Fi router. It takes those packets from the network layer and wraps them into something called a frame, making sure they get across that one single link without any issues.
And finally, we hit the foundation, Layer 1, the physical layer. This is where the digital world becomes physical. This layer is all about the actual hardware, the cables, the connectors, the radio frequencies that turn the ones and zeros of your data into real electrical signals, pulses of light, or radio waves.
And this is what it looks like in the real world. That physical layer is your data literally flying through the air as radio waves on a Wi-Fi network or pulsing down a physical Ethernet cable. They're just different methods for moving those fundamental ones and zeros from point A to point B.
Let's just take Wi-Fi as a quick example. You've probably seen these codes like 802.11a, b, or g on your router box. Well, they aren't just random letters. They represent real trade-offs. Some, like A, were really fast but had a shorter range. Others, like B, were slower but could go further. The newer standards are always trying to find that perfect sweet spot between speed, range, and cost.
Okay, so we've got the data all packaged up and sent out. But in a network with millions, even billions of devices, how does a message know exactly who it's supposed to go to? Well, the answer is in how it's transmitted.
First up, you have unicast. This is your standard one-to-one private conversation. When you're browsing a website or sending a direct message to a friend, your computer is having a unicast chat directly with one single server or one other computer. Simple as that.
Then there's broadcast. This is a one-to-all public service announcement. It's like shouting a message in a crowded room. One device sends out a packet, and every other device on that local network hears it. This is really useful for things like when your computer first joins a network and needs to shout, "Hey, is there a server here that can give me an address?"
And finally, you've got multicast, which is a really clever mix of the two. This is a one-to-many kind of communication. A device can send out just a single message, but only a specific group of devices that have subscribed to that message will actually receive it. This is super efficient for stuff like streaming a live video to a specific group of people without totally flooding the entire network.
So let's just recap the whole crazy journey. You hit send on an email, your data gets created up at the application layer, then it travels down that whole stack, getting wrapped in a new header at each layer like a little digital package. The network layer finds the best road for it to take, and the physical layer zaps it out as signals. On the other end, the whole process just happens in reverse. The message gets unwrapped layer by layer until it shows up, perfectly put back together on your friend's screen. And this all happens in a fraction of a second. It's amazing.
So why does any of this matter? All these technical details, these layers and protocols, why should you care? Because this whole complicated system is so much more than just wires and rules. It is the literal foundation that makes instant communication across the entire globe possible, allowing us to build communities that have nothing to do with physical location.
But let's leave you with this final thought. This whole architecture we've been talking about, its core was designed decades ago for an internet that looks nothing like what we have today. Now we're rocketing into an age of trillions of connected devices, of AI, of these massive virtual worlds. So the real question is, what will the network of tomorrow demand? And is this incredible blueprint we've just walked through, is it going to be enough?
Let's talk about one of the internet's true unsung heroes. It's a piece of technology that works tirelessly for you every single time you go online, but you've probably never even heard of it. And honestly, it's one of the most important players in the whole game. I mean, really think about that for a second. How on earth can your iPhone seamlessly open a document made on a Windows PC? How can your banking app send your most sensitive information across the public internet without everyone seeing it? It feels like it should be chaos, but it just works. Well, the answer to all of that has a name: the presentation layer. So here's how we're going to break it down. We'll start by thinking of it as the internet's middle manager. Then we're going to look at its three main jobs. It's a universal translator, a security guard, and a data compressor. And by the end, you'll see why it's basically your own personal digital bodyguard.
All right, let's get into it. In the big complex map of the internet, what the experts call the OSI model, the presentation layer is layer 6. Now, you don't need to memorize that, but what's important is where it sits, right below the apps you actually see and touch, doing all the critical prep work behind the scenes.
Okay, syntax and semantics. Sounds a little academic, right? But here's what it really means. This layer doesn't care what you're saying, but it cares a whole lot about how you're saying it. Its entire mission is to make sure that when your computer sends something, the computer on the other end can actually read it. It's like the ultimate copy editor for your data.
And that leads us perfectly into its first and maybe most important job, acting as a universal translator. To get it, you first have to understand the problem it solves.
You see, not all computers speak the same language. One might use a format called ASCII to represent letters and numbers, while another, older one, might use something totally different, like EBCD. If they tried to talk directly, it would just be noise, complete gibberish. It'd be like you trying to have a conversation with someone who only speaks Klingon.
So how does the presentation layer fix this? Well, the solution is actually pretty genius. Instead of creating a separate translator for every single possible language pair, which would be a nightmare, it establishes a common language. It takes the data from the sender, translates it into this universal format, and then translates it from that common format into whatever the receiver understands. So think of it this way. On your end, the presentation layer is an encoder. It takes your message and encodes it into that neutral, common tongue. Then, after that message zips across the network, the presentation layer on your friend's computer acts as a decoder, translating it back perfectly so their machine gets it. It's a simple idea, but it's incredibly powerful.
And the result? Honestly, it's nothing short of magic. It's the reason you can open a photo or a document from anyone, anywhere, without ever stopping to think, I wonder what kind of computer they used. This interoperability is the glue that holds our digital world together. Okay, so making sure everyone can understand each other is huge. But what about the conversations you don't want everyone to understand? What about privacy? Well, that brings us to the presentation layer's second big job, being your security guard. This is a question that affects every single one of us. Every time you log into a website or buy something online, your information is flying across a public network. So what stops a bad guy from just plucking it out of the air? The answer is one powerful concept: encryption.
Encryption is basically the art of taking your readable message and scrambling it into total nonsense that no one can understand. The presentation layer does this on the sending end. Then, on the receiving end, it uses a special key to unscramble it back into its original form. Without the key, it's just garbage.
To make this real, let's look at a classic example called DES, the Data Encryption Standard. Now, this was a huge deal for decades. It was the standard for protecting a ton of government data.
So, how does something like DES work? Well, it chops your data into small blocks and then, using a secret key, puts it through an intense 16-round scrambling process. Think of it like a digital maze. By the time the data comes out the other side, it's so twisted and transformed that it's completely unrecognizable.
And here's the really elegant part. It's symmetrical. The complex process used to encrypt the data is essentially the same as the one to decrypt it. You just run it backwards. It's a beautiful, efficient design that was a cornerstone of data security for years, all happening right at the presentation layer.
So our data is now understandable and it's secure. What else could this layer possibly do? Well, it has one more pretty amazing trick up its sleeve: making your data smaller. And this is absolutely critical for the internet we use today.
Data compression is exactly what it sounds like. It finds clever ways to represent the same information using fewer bits. It squishes the file down, removing all the unnecessary parts so it's lighter and nimbler. And a smaller file is a faster file.
Why does that matter so much? Do you like streaming movies, listening to music on Spotify, sending videos to your friends? None of that would be possible without compression. A high-def movie would take, days to download. Compression is the secret sauce that makes our high-speed multimedia world go round. So let's put it all together now. When you look at these three jobs, translation, encryption, and compression, you start to realize the presentation layer isn't just a middle manager. No, it's way more than that. It's a full-on digital bodyguard for your data. Think about its checklist. First, translation.
Is the data understandable? Check. Second, encryption. Is the data private and secure? Check. And third, compression. Is the data small and fast? Check. It literally prepares your data for anything the internet can throw at it.
This really just says it all. It's the silent workhorse that makes sure our digital lives are universal, private, and efficient. Every single email you send, every video you watch, every purchase you make, it's all relying on this invisible layer doing its job perfectly, every single time.
And that kind of leaves you with one last thought, doesn't it? The presentation layer is just one hidden piece of this enormous, complicated puzzle. It really makes you wonder, what other invisible heroes and incredible systems are firing away right now, right behind our screens, making our digital world possible? It's a pretty amazing thing to think about. Thanks for tuning in.
All right, let's talk about the part of the internet that you and I are using right this very second. We're going to pull back the curtain on the layer where all your favorite apps live and breathe. This is the very top of the networking stack, and honestly, it's the most important one.
So here's our game plan. We'll kick things off with what this layer actually is, then we'll get into the rules that make it all work. After that, we're going to map out the entire 7-layer journey our data takes, see how it literally travels through the world, and then we'll circle right back to what our applications are doing before we wrap it all up with why this stuff really matters. Okay, let's jump right in at the very top. We're starting with the layer that you, me, all of us are using right now to connect to, well, everything.
I mean, think about it for a second. When you open your browser or you shoot off an email or you hop on a video call, that whole process doesn't start down in some cable or in the Wi-Fi signal. Nope, it starts right here with the software that you're touching and controlling. Every single thing you do that uses the network begins at the application layer.
And that leads us to the big idea. Now, officially, yeah, it's called Layer 7 of the OSI model, which is just the standard way we talk about network communication. But you don't need to be some network genius to get this. Just think of it as your browser, your email app, your games. It's right there in the name, your applications. It's our window between the user and the network. It's how we see and interact with everything out there.
So what does this window actually let us do? Well, it provides some really crucial services. It's what handles file transfers, right? That's how you download a PDF or sync up your cloud storage. It's the engine behind your email, making sure your messages get sent and received. And it manages directory services, which is kind of like a big address book for finding stuff across the network.
Okay, so our apps give us these amazing services, but how do they actually talk to each other? I mean, your web browser has to communicate with a web server halfway across the world. They can't just shout into the void and hope for the best. They have to follow a very specific set of rules. And this is a huge question, isn't it? You've got billions of devices from thousands of different companies running all sorts of software. How in the world do they all manage to communicate so perfectly?
And the answer is protocols. You can think of a protocol as the shared language and, the proper etiquette of the internet. And this is the magic right here. These invisible rules are the only reason any of this works. It's a huge global agreement that lets a phone in Tokyo and a server in Toronto understand each other perfectly every single time. It's kind of amazing.
And these rules are incredibly specific. Protocols define everything. When messages get sent, how big they can be, how they're packaged up, what format they need to be in, how they're encoded, even the exact back and forth pattern of the conversation is all laid out. It's that level of detail that makes the whole global internet possible.
All right, now that we've got our window and we understand the rules of the conversation, let's zoom out. Let's look at the entire roadmap for our data's journey. And that map is called the OSI model. You see, sending data over a network is ridiculously complex. So to make it manageable, it was broken down into 7 different jobs, or layers. We've been talking all about the top one, layer 7, the application layer. But as your data starts its journey, each layer below adds its own instructions. The presentation layer handles things like security. The session layer manages the conversation. The transport layer makes sure it gets to the right app. The network layer finds the best path. The data link layer gets it ready for the physical trip, and then, all the way at the bottom, the physical layer turns it into actual bits, the electrical signals or pulses of light. So let's really picture this. Imagine your email right after you hit send. Think of it taking a trip down a 7-story building. On each floor, it gets a new wrapper of instructions, getting it ready for its final physical journey out into the world.
Because once that data hits the ground floor, layer 1, it's not an email anymore. It's not a photo. It's been converted into raw signals, electrical pulses zipping down a cable, or radio waves flying through the air. This is the moment where the digital becomes physical. An idea becomes a real force moving through the world.
And these are the literal roads that data travels on. It could be a copper coaxial cable, like you see here, with all its different layers of shielding. Or it could be tiny pulses of light flashing through impossibly pure strands of glass in a fiber optic cable, bouncing their way across oceans at pretty much the speed of light.
So after that incredible journey, the data gets to where it's going. And then the whole process just happens in reverse. It travels back up that 7-story building. On each floor, a layer of instructions gets unwrapped. The physical signals turn back into data. That data gets routed to the right application. And finally, it hits the application layer on the server, where your friend's email app can read your message perfectly.
And you know what's cool? These are the protocols doing that final bit of work. And you know these names. HTTP is the language of the entire web. FTP is for file transfers. SMTP sends your email. And then you have DNS and DHCP, which are two of the most important unsung heroes that make the internet just work for all of us every day. Let's take a quick look at DHCP. When your phone connects to Wi-Fi, how does it get an address? It uses this simple 4-step conversation. Your phone basically shouts out a discover message saying, "Hey, I'm new here." A server replies with an offer like, "Here's an address you can have." Your device sends back a request saying, "Awesome, I'll take it," and the server seals the deal with an acknowledgement. This all happens in a blink of an eye, all thanks to an application layer protocol.
And then there's DNS, the domain name system. See, computers talk in numbers, these long IP addresses, but we're human. We remember names like nec.edu. DNS is basically the internet's phone book. When you type in a web address, your computer asks a DNS server to look up the matching IP address so it knows exactly which machine on the network to talk to.
So let's tie all of this together. We've seen that the application layer is our interface, that protocols are the rules of the road, and how this whole 7-layer journey gets our data from point A to point B. So why is this one layer so special?
It really does all come back to this single idea. This is the key. All that complexity, all the fiber optic cables under the ocean, all the routers and switches across the globe, they all exist for one single reason. And that reason is to serve the application layer. It's the whole point of the network. This is the layer that takes all that amazing, mind-boggling technology underneath and turns it into something we can actually use. Without it, the network is just a bunch of silent wires and potential. The application layer is what makes it useful. So the application layer gives us this incredible window to an entire world of information and connection. The only question left is, where are you going to point your window next? Thanks for joining me.